everyone. My topic for today is zkEVM and Kakarot in focus. So you might be wondering what the Kakarot is. I believe by the end of the talk you will be knowing what Kakarot is. Short introduction. I am Venkatesh. I worked with Nethermind for 6 months as a senior solidity smart contract engineer. Right now working with the NCR Corporation as a product owner. I'm into the blockchain space for almost 3 years now, and I'm a chapter lead for the Phoenix Guild community and also a Starknet ambassador. Starknet being the layer 2 blockchain, which is based upon the ZK rollups by a Starkware company, which is an Israel company. Now, before we delve into what the ZK EVM and EVM, let us begin with the first principles. What is a virtual machine? By definition, it is a software program which will be running the instructions in a loop of whatever instructions that were given to it, and it will kind of mimic the physical machine, like read, interpret, and execute the instructions. So, physical machines, you will be everyone will be aware of it. CPU, we call it as a physical machine, which will be present in every hardware devices. Which what it does is actually it reads, interprets, and executes the instructions that are given to it. When I said instructions, what is an instruction and what is an opcode, and what is an opcode arguments? Instructions of a CPU can be like a task that we ask the machine to perform, like and it has to be a low level task. It's not like you can give that make a network call or a capture my keyboard strokes. These are the high level tasks. These are not the tasks which we can ask the CPU to perform. So the instructions has to be low level one, like add 2 plus 3, like adding the two numbers and storing the results in either registry or the stack. And opcodes is how the instructions are run on the CPU. That means because a machine will be understanding the binary ones, zeros, and ones. So these opcodes will be internally converted into the hexadecimals and into the binaries. So, and EVM is no different. EVM do have its own instruction set, which was when we all the instructions that are part of the EVM blockchain, Ethereum blockchain and EVM machine is written in the Ethereum yellow paper with the Gavin word. And opcodes, this I spoke. And when we write the smart contracts for the Ethereum in Solidity, and when you compile it, we get the bytecode, which is an hexadecimal one. That is what that gets stored on the blockchain. So the this and this bytecode is nothing but your instructions or opcodes that were given. This is the one EVM is going to look at these hexadecimal ones, and these hexadecimals are nothing but the opcodes, which internally while executing will be converted into the binary. Suppose, for example, the bytecode for a small smart contract program is there, and 0x2 is nothing but a push 3 opcode, which tells to push next 3 arguments from the 6 to the stack to execute it. And the other beauty of it is the arguments follows the opcode. When I say push 3, what the program control does is from the opcode it pushes next 3 bytes onto the stack to execute the things. This is some brief about how the bytecode and everything is. And this one, you might be wondering how long this execution is going to continue. If we pass the bytecode to the EVM, you might be, it is going to execute as long as the bytecode encounters a return opcode, or it encounters the stop opcode, or you might be, the transactions in Ethereum are atomic by nature, and if it reverses crashes by any invalid opcodes or some other things, then also the program is going to be stopped, and PC reaches the end of the opcode. Like this is the length of the opcode. When the program reaches the end of the opcode, then that's how it's going to stop. And also the other way is when it runs out of the gas. We have to perform a certain operation, but we are not providing the amount of gas, so it would be stopping. That way, I believe why this is designed in such a way is to mitigate the denial of service attack. Because unlike CPUs, normal machines which will be executing trillions of instructions per second, EVM is not designed for that. EVM is not executes only a few opcodes or instructions per second, and to prevent the denial of service attack, it has a metering mechanism called as gas. And this is an example wherein, as I said, execution is linear. Linear in the sense it doesn't mean that it will continually going up. The program counter is going to from one opcode to another in a linear fashion. It might, if it encounters certain opcodes like in EVM we have jump and jump F, the program counter can come again to the first position and can start executing from that. This is a kind of a EVM challenge, and how we can do this EVM understanding if you are to do the things. And before we go to the zkEVMs, just now it spoke, understood on a high level what the virtual machine is. Now we talk about the zkEVM. Before we move into the zkEVM, zk virtual machine is nothing but it's a circuit for the zero knowledge proof system. So ZKP being a lot being spoken now from almost 1 or 2 years. So you might be knowing what zero knowledge proofs is, wherein the prover is going to prove to the verifier that he knows certain piece of he knows the information just by providing only a piece of it, thereby achieving the privacy, because he is going to provide the only piece of it, not the full. And also zero knowledge proofs helps us to or do the off-chain computation, thereby allowing us to execute many, prove the computation and take the computation off-chain and only put the data onto the proof, or only proof onto the on-chain. That is one way. And zkEVM, as I said, it's a circuit. When I said circuit, it's an algebraic circuits wherein you have the physical gates which does the add and multiplication only, and your program will be converted into a statement. A statement will be again converted into a polynomial, and this particular polynomial will be converted into an algebraic form, which gets executed to provide, which gets executed and provide you the proof. Unlike EVM, which will be executing the transaction, zkEVM is going to prove the execution of the VM. And when I say zkEVM, it is going to it's taking the CPU approach. There are two kind of approaches for the zkEVMs. You can take the hardware approach, whereby you can specifically design the specific ASICs or FPGAs to perform the zero knowledge operations, or you can take the CPU approach by writing the software to get the proving and verifying code. So zkEVMs take the CPU approach, unlike the hardware approach. And I have listed few zk virtual machines. One is the Cairo VM, which is by the Starknet, which is a kind of, it's not EVM, it's a zkEVM, because it doesn't take the Solidity byte code and runs the transaction. It will not understand it, because it's not the EVM, it's the VM, and it has its own domain specific language, what we call it is a Cairo, which is based upon the Rust. So, and Polygon Maiden is one example again, and RISC-0, which is based upon the RISC-V instruction set. So these are the zkEVMs, which has its own programming language to write the smart contracts. And types of zkEVMs, when I was speaking about the zkEVMs, it can be classified into two. One is the zk optimized VMs, and another one is the real world VMs. When I say zk optimized VMs, it is optimized for the zero knowledge things, generating the proofs and other things, because generating the proof is a costly affair, wherein a lot of computation will takes, and in turn it will lot of amount that is going to be spent. So Cairo and Maiden falls into the zk optimized VMs, because it is optimized for the zk, not for the EVM. Whereas the real world EVMs are kind of like we call EVM compatible or EVM equivalent virtual machines, they fall under this real world VMs like Polygon Hermes, which is an zkEVM, because it understands the solidity bytecode to execute. Now coming to zkVMs, we have coming from VM to zkVM, now to zkEVM. By definition, it says it's a virtual machine that can execute the smart contracts in a way that's compatible with both zero knowledge proof and existing Ethereum infrastructure. And this enables them to be a part of the rollups, and which is a layer 2 scaling solution that can increase the throughput and lowering the cost. So I mean, the origin of the zkEVM, so we can say, is coming from the blockchain's trilemma issue, wherein we can achieve only two things. We need to sacrifice the third one. So to have the scalability, in order to have the scalability, provide the scalability to the Ethereum, we have coming with the zkEVM things. This is when this slide has to be before the zkEVMs. Within this slide is telling you that what it contains. We have the hard. It can consider. You can think of a node having a node runner will having a hardware, and on top of it he would be running the Ethereum node, which is Geth or some Nethermind ETH, and on top of it he is going to have the Ethereum virtual machine, a software program which understands the EVM bytecode to execute the transactions. I was talking about real world zkEVMs and zkEVMs. While I was talking about the real world zkEVMs, we need to take some consideration into picture. Like, we cannot design the zkEVM on the EVM itself, because it's very tough. Because EVM by specific, when it was designed 9 years back, it was not taken into consideration of generating the zero knowledge proofs. Because if you try to do if you wanted to modify the existing EVM for the zk purpose, it will be a huge cost affair, because to generate the proofs, it will be a computing intensive one, and it will be cost effective one, and it will just break the design why it was designed for. So doing it on EVM is I think it's not cost feasible, and also a lot of design constraints that comes into picture, because each opcode will have certain amount of gas to spend, as described in the Ethereum yellow paper. So we have to tweak a lot of things, like each opcode has a list of gas that can be spent. So we have to tweak the gas amount of gas that it going to be spent by each opcode also, to either to increase the efficiency of proving things and doing that. If we do that, what happens? The existing dApps or smart contracts that are deployed with previous version of the gas metering will break. So there will be a lot of breaking changes. So we take this away from the EVM when we build a EVM outside the EVM, zkEVM, to have in order to prove lower the proving cost and the verifier costs. So this particular slide tells you that you can have the EVM at a language level compatible one, and the bytecode level compatible one, and consensus level, and how hard and how good it is to have this compatibility. If we language level compatibility is very easy to achieve, because it is zero knowledge friendly, like Cairo VM, wherein it will take the solidity code and transpiles into a Cairo, which again transpiles into a Sierra assembly, which understand by the Cairo VM. So that's way it is easy to work, not the hardest one to achieve the language level compatibility of zkEVMs, but it's bad if we take it from a design perspective. And another one is you can have the bytecode level compatibility. Like if you give the same bytecode which was generated by the Solidity to the zkEVM, which is of a bytecode level 1, I believe Scroll is the one which trying to build a bytecode level compatibility zkEVM. So here you don't, I mean, it understands same, I mean, with if you want with the bytecode level opcode compatibility one, you don't have to write the smart contracts in different language or transpile into a different language. The same bytecode can execute, and the advantage of it is it has a composability of supporting the previous dApps that are already deployed in the EVM. It is the same, right? Whether it is executes on the normal EVM or the bytecode level compatible zkEVM, it's the same bytecode. It will in fact generate the same state in the sense, if you give the same inputs to, and it will compute the, I mean, it will do the same hashing everything, and it will generate the same hash at the end of the route. So it will be like state of A is equals to state of B. And consensus is very ambitious, but it's damn difficult to achieve. So I don't think no company is trying to do this as of now. This slide tells, as I said, if you wanted to stagnate a Starkware, which is a zkVMs, what it does is it takes the solidity, transpiles into it Cairo assembly. It has its own instruction set because it's another zkVM, it's another virtual machine altogether. So it has to have its own instruction set and it's in the same assembly. In the same way, it's the Zinc as well, zkSync. And this slide tells you different companies are doing zkEVMs and what it can offering. Like if you take the zkSync, it has the general purpose one. Scroll is also a general purpose programming thing, and Polygon also, and Starkware. Cairo, though it is specific to the zkEVM that is designed by it, it is actually a general purpose programming language wherein not just smart contracts, you can write the smart contracts for the Starknet, but you can also write your general purpose programs, like you can write the Fibonacci number and any other number. That's where we are calling it as a general purpose. So native solidity support, see, you can only have it in the Polygon, Scroll and zkSync because they are somewhat bytecode compatible ones. Starkware is not going to have it. Account abstraction, only zkSync and Starkware. Starkware, by default, it has an inbuilt native account abstraction built in, so it will be taken care of. Yeah, open source, zkSync and Scroll is open source. I don't, I mean, Polygon is open sourced it, prover and verifier code, but Starkware during its Starkware sessions in February has decided to open source its verifier and prover code. So that is going to happen soon. So it will come under the category of the open source as well. In native Ethereum, Solidity will be again converted into the EVM bytecode, which is executed by the EVM, and the bytecode compatible EVMs, the Solidity EVM will be converted into the EVM bytecode, and it will be executed by the zkEVMs. Whereas language compatible zkEVMs, the Solidity will be converted into some other programming language of its, which will compile and create a VM bytecode which is specific to the zkEVM, wherein Cairo comes into the one example. And this another slide tells you what is the runtime under the hood of each company that is making the zkEVMs, and what is the bytecode that expects by these zkEVMs, and what is the language that they chose to write their smart contracts for their zkEVMs. These are the few companies like Starknet, zkSync, Hermes, Scroll, which is trying to build the zkEVMs with its own unique approaches. The slide is taken from the Vitalik's zkEVM blog post, wherein he divided the zkEVMs into different categories or types. Like we have a type 1, type 2, type 2.5, type 3, type 3 and type 4. We can come from the down at what is a type 4. Type 4 is nothing but a type 4 zkEVM is similar to a language compatible zk virtual machine. here you can take an example of StarkNet, because it has its own language. Solidity is not going to be supported natively. Solidity has to be converted into transpile. The advantage of it is because it is designed for the zk specific one. The amount of time it takes to generate the proof is very less, maybe in seconds or in minutes. Now going forward, going little up, type 3. Here it is compatible with the Ethereum apps and can share a lot of AVM infrastructure, and it can generate the fast ones. But the environment, I mean, is a little bit different, because it is not going to support all the EVM functions. I mean, like EVM has different hash functions like HAC 256, SHA-256, and it also has the precompiles from address 1 to 9. So it is not going to support those things, but other opcodes, it can support other opcodes which are supported by the EVMs. Those zkEVMs will be falling under the type 3 one. Now you can, I mean, there are certain zkEVMs which support a little ahead, like it can support the precompiles but not the hashing functions, so they fall under the category of 2.5. Kakarot, which is a zkEVM built on top of the Cairo virtual machine, falls under this one. It has support for almost all the I think almost all the opcodes and also the precompiles. Now type 2, if you go little up, it has a type 2. This is, I mean, it's fully compatible kind of a thing, wherein it has support for all the opcodes including the precompiles. Polygon Hermes is trying to do this, so Polygon Hermes is a type 2 zkEVM. Now the most ambitious one is the type 1, which is kind of, I mean, what the EVM does is also can be done by the type 1 type 1 zkEVM. But the disadvantage is the proving to generate the proof for the zkP. It takes a lot of time. I mean, maybe 10 minutes or 15 minutes. If you wanted to do the transaction and if you wanted to wait for the proof to generate the 15 minutes, I don't think you will wait it. So I think it's an ambitious one. Unless we crack it to some means of generating the proof in, I mean, in a way it type 4 zkEVMs does, then only it is going to sustain. Yeah, this kind of summarizes what I spoke about different types of zkEVMs, like source code, bytecode compatibility, and 100% API gas calculations, how it was done, and the block root. And the last column tells you which is good one, which has a performance one. Type 1 has a very low performance because the amount of time it takes is damn high. The type 4 is the one that has to be chosen if you wanted to go for the zkEVMs and if you wanted to have the fast performance and fast finality and high throughput. Coming to the Kakarot, I, being a StarkNet ambassador for the Starkway company, I have delved a lot into the StarkNet ecosystem. So, because the topic is the zkEVM, so Kakarot is an implementation of the EVM developed using the Cairo programming language. As I said, StarkNet has its own language, domain-specific language. We call it as a Cairo. So we have taken the Cairo programming language and we have written kind of mimic each and every opcode of EVM. We have taken the add, mul, ECT cover, everything, and we have coded in Cairo. So if you call it, it automatic. I mean, if you supply the EVM bytecode, it will execute as if you are executing it on the EVM. So right now, it is written in the Cairo 0, which is kind of a hard one to learn and code. I mean, only some geeks would have done that. So what the StarkNet has done is it has moved from its earlier design of language, which is a bit of assembly, to a Rust based one. We call it as a Cairo one, which is a bit easy if you know the Rust language. So Kakarot is now again migrating from the Cairo 0 to the Cairo 1, and Kakarot is an open source project wherein if you know the Rust programming language, learning Cairo 1 is very easy because it's compatible one. So you can come and contribute and get paid for that because StarkNet Foundation does that. And the main, coming back to the Kakarot, the main difference factor for an EVM written in Cairo is that its transactions are provable, unlike native EVM transactions, because Cairo is a general purpose provable programming language. When I say provable programming language, when it executes a program, it not only generates the result, but it also generates the proof of the result. Like say why it is needed, why a provable programming language is needed is, suppose you have, I mean, we have a big program for with us, a big programming, and we wanted to execute it, but we do not have the resource for it. Like say we might need a supercomputer to execute our smart contract. So only our rival country, which is, which may, in example, say we have China has the capability of executing that particular programming. So we can ask them, and he will run the program and he will give the result. I mean, at the end of the day, you take the result. Do you know? Does he did not edit or modify the program, and the result that got generated by executing that particular program given by the rival country is a trustable one? No, he might have done it. If we just rely on his result output, and if we take it as it is very difficult. So what the Cairo does is, being a provable programming language, when it executes the program instruction by instructions, it takes care of generating the proof of the result. So at the output of the Cairo programs is a result and how the result are achieved. If you modify it, the proof that gets generated at the end of the day, end of the transaction, is a different one. So if we ask the rival country to execute the Cairo program, then it will going to give you the result as well as the proof. Then we can, I mean, verifying the proof is easy than the generating one. If you understand the zk architecture, verifying thing is easy compared to the generating. So if the rival country would be giving the result and proof, what we can do is just verify the proof. Proof is verified. That means the program is not modified. Then we can use it. The result can be used one. So that a bit of history about the Cairo. When I said it's a provable programming language, wherein EVM was written in the Go language, whereas the Kakarot is written in the Cairo language. Cairo being, as I said, it's trying to achieve almost a good compatibility one. So it's right now it is falling under the type 2.51, which is a good one, and it's scalable. Again, this can be achieved using the zero knowledge proofs, wherein you can do the computation of chain and only post the state to the L1. And secure. Security being building on the EVM can be derived from the L1, which is Ethereum. Now this is like, at the end of the day, what the Kakarot is. A Kakarot is nothing but a smart contract written in Cairo, deployed on the Starknet blockchain. So what it does is, this is a flow of how the transaction can flow. Alice is sending the EVM transaction or EVM call to the Kakarot RPC, which will a Starknet JSON RPC. What it does is it wraps the EVM transaction with the user Starknet account address, and it goes to the Starknet blockchain, where you have the sequencer. The role of the sequencer here is to batch or order the transactions that gets executed, and this Starknet sequencer then can do some verifications like the signature verification, other things. After that, if the verification of the transaction is passed, then it is moved to the Kakarot smart contracts, because it's the same bytecode at the end of the day. Because the Alice is doing the EVM transaction call, not the Cairo one. So because Kakarot is trying to be an zkEVM compatible one from the bytecode point of view. It is trying to achieve the bytecode compatibility. That's where Alice was sending the EVM transaction, not the other transaction. So this, at step 7, After passing the verification, it will take the bytecode and it will execute the EVM bytecode and generate the proof to be I mean, at the end of the day, Darknet is nothing but a zk rollup, which will do the batching of transactions outside the L1, thereby achieving the good throughput as well as a fast finality. And what it does by batching those transactions, in the sense like executing those transactions, after all executing the transaction, it will generate a proof of that particular batch, and that proof is going to what gets verified on the Ethereum. Like I mean, so what the Starknet does is we have the verifier.sol smart contract, which is in Solidity on the already deployed in the EVM blockchain. So after doing the computation, after generating the batch proof, this proof is sent to the verifier.sol. What it does is it verifies the that particular proof and updates the state on the L1. So thereby trying to maintain the state of it. This is brief about zkEVM and Kakarot. If you have any questions, welcome. Yeah.
My question is that you mentioned that there are some trade-offs when we move from type 4 to type 1, right?
Yes.
You have poor performance and then you have full compatibility.
Yes, exactly.
So, I'm aware that everyone is trying to improve the poor performance a bit so that they can move towards type 1. But how feasible do you think it is to modify the EVM thing so that there can be a middle ground?
It's not feasible by the CPU approach. We need to have the hardware support as well, because a lot of hardware companies are manufacturing the specialized ASICs and FPGAs. If you have it, the amount of time it gets generated, proof get generated is very fast. So without the support, I believe hardware support, getting a type 1 kind zkEVM is not feasible.
Yeah, but so my question is that, like, instead of extending the prover performance to make it reach type 1, is it possible to change the EVM spec so that there is some middle ground?
You cannot just go and
Yeah,
edit this
I'm
pipe,
aware
right?
that.
You need to have the backward compatibility, and taken the consideration that EVM is the most popular one and a dominating blockchain. We are not going to do that.
Okay.
What we can do is day by day we can I mean, there was a lot of research every day, almost 10, at least 10 new research papers gets published in the zk domain. So everyone was doing a lot of research trying to do something that uh, gets us to generate the proofs in a CPU approach in a very faster way. So we are so early, and we have a lot of optimism that after going down the line at 2 to 3 years, we might be there.
Thank you.
Any more questions?
So is Cairo similar to this language called zkEVM?
Circum is a circuit programming language. When I was showing the zkVM slide, I mentioned zkVM is implemented as a circuit. Circuit in the sense, it's kind of an algebraic structure wherein you code the polynomial in a certain programming language. Circum is a circuit programming language which will be useful for the core programming of the zkVM.
So it's like
That's
Cairo
correct.
is for the infrastructure level and zkEVM is for the DApp level, application level.
Yep, exactly. Yeah, I thank you for listening patiently to my talk.